A random sample of 600 fans were selected to view the audition tapes of 12 never-before-seen contestants. For each of the fans, the order of the 12 videos is randomly determined. For each fan, thus, the order of performance doesn't matter. We expect 1/12 of the fans to prefer the last contestant. Because if there's 12, then you got a 1 in 12 shot. In the study, 59 out of the 600 liked the last contestant they viewed. Does this data provide convincing evidence that there is an advantage to going last? So step number 1, we state our null hypothesis. So in our case, HO is where our P is 1/12. And HA is where our P is more than 1/12. Because we're trying to show that going last gives you an advantage, which means the probability should be more than that. Or the proportion, excuse me. And we're going to define our P as the true proportion, or proportion, I guess you could say, of idle fans who prefer the last contestant. Is where we talk about the plan. So in our plan, we talk about the test first. We will do a 1 sample Z test for P at, and again, they did not tell us our significance level, so we say alpha equal to 0.05. We have a random sample of 600 idle fans. So now we've talked about the test, we've talked about it being random. Now we talk about the normalness. Is NP greater than or equal to 10? So we take 600 times 1/12 to see if that's greater than or equal to 10. So 1/12 of that is 50. So that's good. We take N times 1 minus P and see if that's greater than or equal to 10. So that's 600 times 11/12, which would have been the remainder, 550. And see if that's greater than or equal to 10, and it is. So now we know that our stuff is normal. And lastly, we want to know if there's at least 10 times this number of fans. So I would say it's reasonable to assume there are over 6,000 idle fans. So we have independence. So in our math part, we need to find our z first. So we know that our z is equal to p hat minus p0 all over the square root of p0 minus, or times 1 minus p0 all over n. And in our case, that would give us 0.0983 minus 0.0833. You could use fractions if you want, so you don't have to have the decimals that I have. And then down below, inside the square root, the decimals that I get are 0.0833 times 0.9167. That's the 1/12, 11/12. And there was a sample size of 600. And so that gives me a z-score of 1.02. 1.13. If I'm drawing this picture, and we know that our z is 1.13, and we are trying to say that it's more than that, that means we're shading off to the right. So then to find your probability, you would say that your probability is the probability that your z is going to be greater than that 1.13, which is equal to the normal CDF of 1.13 comma 99, which was equal to, in my p-value, I got 0.0912. And if you want to show off to the side, I think you could leave it just like that. But you could definitely, if you wanted to, talk about how you found your p-hat, where you had the 59 people out of the 600. And that was the same thing. So this p-hat right here, in fraction form, is the same thing as this 0.0983. So here I wrote it as a fraction, but up above in the z I wrote it as a decimal. You can do it either way, it doesn't really matter. So this gives us the p-value, and then down below, the last thing that we're going to do, of course, is we're going to talk about what we conclude. So we say our sample of 600 fans, or idle fans, I guess more specifically, with a proportion of 0.0983 would occur 9.12% of the time if the true proportion is 1/12. Since our p-value of 0.0912 is greater than our alpha, which was equal to 0.05, we fail to reject our null hypothesis. We conclude that there is no evidence that going last gives a contestant an advantage. And then we'll move on to the next one. So a couple of errors. First of all, the one up here where the z-score was 1.13 was actually 1.33, I'm told. So down here, that's also the same, 1.33. Which then would change the p-value down below to 0.0914, I'm told. So when I change that in my percentage, this is also a 4 over here, and a 4 over here. And our conclusion turns out to be exactly the same, so sorry for the error on there, 1.33 for the z-value. So in example number 3, when an accounting firm called AJL and Associates audits a company's financial records for fraud, they use a test based on Benford's law. So for those of you going to business, you'll probably study this. It states that the distribution of first digits in real-life sources of data is not uniform, or in other words, is biased. In fact, when there isn't a fraud, 30.1% of the numbers in the financial records begin with the digit 1. However, if the proportion of the first digits are 1 is significantly different than 0.301, in a random sample of records, AJL and Associates does a much more thorough investigation of the company. Suppose the random sample of 300 expenses from the company's financial records results in only 68 that begin with the digit 1. Should they do a more thorough investigation? Oh, you don't have 300? Write that in, please. Sorry. So right here, add that in. I think that went to print before we actually amended it. So add in the stuff. So in this case, this is saying that my null hypothesis in the stating part is that my proportion is supposed to be 0.301. That's what's going on. Our alternative then, in this particular case, is that we want to know if that's not true. So we say not equal to 0.301. And this P is equal to the true proportion of expenses that begin with a 1. We will do a 1 sample z-test for P at alpha equals 0.05 because, again, they don't tell us the significance level. We have a random sample of 300 expenses. And we check to see for normality, so we take the NP stuff and see if that's greater than or equal to 10. And remember that P is the P0, the P from our paragraph up above. So that's 300 in our sample times the proportion, which we said was 0.301. To see if that's bigger than or equal to 10. That should give me, I think, 90.3. So we can check the math on that. And that is bigger than or equal to 10, so that part's good. We do the N times 1 minus P to see if that's bigger than or equal to 10. Or in other words, 300 for the sample times 0.699. Let's see if that's greater than or equal to 10. And I get 209.7. And that's bigger than or equal to 10. So that's good. And this part shows that it's normal. And then, to show independence, oh, you dirty dog. Okay, I don't really know what's going on there, but that's funny.
Calibrate.
Yeah, whatever. We assume that was the company's name JBL, AJL, that AJL has more than 3,000 expenses. So independence is shown. And now we can move on to the math.